we begin with the question that Shodrik asked in the last class, to take an example of a spanning set and to show you how we throw away elements. Okay. So suppose, take the easiest kind of vector space, say we are considering R2, okay, and take these vectors maybe 0, 1, then 1, 2, okay, 3, -1, and some other thing, say 2, 3. Okay. So suppose this is your original set, okay, and well, at first, suppose we were given that this set spans R2. Okay, we'll later see why. But what we are trying to do now, so this is the spanning set. What we are trying to do, we want to reduce this set to some linearly independent, I mean, to elements which are linearly independent from one another. So a linearly independent set. Okay. What we do, well, this is the last vector. We would like to at first write it in terms of the first tree, okay, if that is at all possible. Okay. So what we do, 0, 1 times some C1 plus C2 times 1, 2, yeah. You can just email me that you are any of, okay, so please. C3 times 3 minus 1, and we are looking for such relations, okay, that some linear combination of this, whether it is giving this or not. Okay. So we would write this then in this form. This is 0, 1. We are just putting this all together, 1, 2, 3 minus 1. This times this one, C1, C2, C3. This is giving you 2, 3. Okay. Because you see, this is nothing but you are taking the linear combination of the first column, the second column, and third column. And you could write this precisely in matrix notation in this form. Okay. And then it's like solving this equation for C1, C2, and C3. Okay. And how do we do this? You must have learned this in the previous semester. Yeah, row echelon. So what to do now? Tell me. Yes, but on which matrix? Just on this one, or do we do something else with this? Very good, Trishit. Yes, that's one. 0, 1, 3, 1, 2, minus 1, and this augmented matrix 2, 3. So let's row reduce this. Okay. Well, you see that first one is there is already a pivot, so you can just flip it. Okay. So this becomes, and this goes to this matrix then 1, 2, minus 1, 0, 1, 3, and this one should also be flipped. So 3, 2. Okay. Now you want to make this a pivot, and that's why this should be removed, right? So he's coming. All right. So Shamanjit, what we did is that we want to write this last vector as a linear combination of these three vectors. Okay. And in the matrix notation, this would be writing this last vector as a product of this matrix times this matrix, because this is giving you C1 times the first column, C2 times the second column, plus C3 times the third column, equal to this one. Okay. And then we are solving it by row reduction. Okay. So we augmented this, and then we are finding out the pivots. We flipped it. The first pivot is already there. Now we are trying to make this one a pivot. Okay. So we have to make this one 0. Right. So 1, 2, minus 1. Well, we can immediately do this. So we can just multiply it with minus 2 and add it up. So So if you multiply with minus 2, this one becomes 0, this one becomes minus 3, sorry, minus 7, right? Minus 7, thank you. And this one is just 0, 1, 3. Okay. Saidam, please write. Saidam. Okay, thank you. So this one, okay, and what we do here, we multiply it with 2 and do minus 1 here. So this would be just 1 and this one 2, right? Right, yeah, thank you. Yes, because it is, sure, yeah. And yeah, so this is our row reduced form, right? Here you have a pivot, here you have pivot, you don't care about this one because you cannot reduce this row in, well, you can reduce the first one, the second one, but for reducing this you need another row, which is not there, okay? But note that now you can put values to, the variables corresponding to this pivot to this pivot. For this you do not care, okay? So you can just put 0 there. Okay. And then what happens? So this will just give you that C1 is equal to minus 1, C2 is equal to 2, and C3 you can just put 0 there, okay? So what happens then? Let's check now. If you put C1 equal to minus 1 times this vector 0, 1 plus 2 times the second one, that is 1, 2 plus 0 times the third one, that is 3 and minus 1. This is giving you, whether this is giving you the right hand side. Okay. So this is just minus 1 at the bottom, this one is 2, and here you are having 4. So you get 2 and below 3, right? So indeed we see that this vector is in the span of these ones, okay? Now note that only the first two sufficed to write this, right? So actually you can do the same thing, but the augmentation could be not only the last column, but you can augment the last 2 columns and see what happens there. Okay. So what will happen then? If you just augment these 2, the last 2 columns, then in one go you will have linear combination, express this as a linear combination of this as well as this one as a linear combination of this one. Okay. So let's do that. Yeah. Oh, why we do this? Because we would then like to throw this away, okay? Because it is in the span of the rest, okay? And then you do the same experiment with these 3, okay? All right. So in fact you can see it already from here, because if you are working with the first 3 and trying to throw away the third one, then you do the same operations, you do the row reduction, you get this one in the first 2 columns, whereas this one will be the third one, okay? So instead of just writing it here, you are writing it there, okay? So what I want to say is that, so forget about this part now, because now what we are trying to do, we are trying to write, instead of C1, C2, we are now trying to do C1, C2 here. Say this is the first column, so C1, 1, C1, 2, C1, 1, C2, 1, C1, 2, C2, 2. Now we are solving this one, okay? This one times this is equal to the last 2 columns, okay? So 3 minus 1 and 2, 3, okay? 3, yes. Right. So what we are doing is that we are just giving an example of, we said that if you start with a finite set, you end up with a I mean, with this algorithm, you end up with a basis. The set which is, I mean, the minimal set should be linearly independent. That we proved in the last class, right? Yes. Yeah. It's what again? Yes. Indeed, indeed, yeah. So you want to, instead of just looking whether this is in the span of this, you want to see whether there is any linear relation at all. Definitely, that works. It will be then up for. Indeed, yeah. And then you can directly apply the exercise that you have done in the first test. That is, if you have, I mean, the number of equations is less than the number of variables, you always have a non-trivial solution. You can just directly apply that thing. Okay. Definitely, that works. Trishit.
Sir, are we augmenting that, like we are creating that matrix after we are done with this, or we are creating it at first, very first?
No. We are, so at first we are going one by one element. That was the algorithm that we.
The algorithm wants to throw that away completely, right?
Yes, throw this one away completely. But what I am trying to say here is that, I mean, the way we did it, we could have actually started with, because we are having the first two pivots in the first two columns. It might have been that we are not having pivots in the first. I mean, that we are having just a matrix, row reduced matrix of this form, 0, 0, 0, 0. So you don't have any pivots in the second column. Okay, and here some other things upstairs. Okay, so that would be just a rank 1 matrix. Okay, but suppose you are in such a case, then what we are trying to say is that you can throw away the last two elements in one go. Okay. If you have a solution to this. Okay. And yeah, what your Mandeep, right? Monodeep. Yes, Monideep. Sorry. So Trishit, what Monideep said is indeed is perfect. That is, you take the entire thing, you add C1, C2, C3, C4 here, and then you are trying to row reduce this one. Okay, so if you are trying to row reduce this one, then and even exactly, and how many pivots could be there? There could be at most 2 pivots, right? So that's why, I mean, this one will always have a non-trivial solution. Okay. But doing this in this manner will have something. I mean, we are now writing this in a matrix form because we'll do something similar in a moment to some other problem. Okay. So let's, yeah, I mean, how we proceed with this, instead of just augmenting this one, now we are augmenting these last two things, right? We are writing that C1 plus, well, the first column, so C11 plus C12, wait a minute, no. Okay, let's write it down somewhere here. So what this equation exactly means, in terms of linear combinations, it is 0, 1 times C11 plus C21 times 1, 2. So you are taking linear combination of these two vectors, and the first column is giving you 3 minus 1. Okay. 3 minus 1. And the second column would give you C12 times 0, 1 plus C22 times 1, 2. This is giving you the last one. Okay. 2, 3. Okay. So we are trying to solve this in terms of C11, C12, C21, C22. Okay. If we have this, then we can say that both these and these are in the span of these two, so we can throw both of them away together. Okay. And for doing that, how should we proceed? We are just putting these two things in the augmented matrix. and we reduce this part. Okay. So things go exactly like this. Instead, just the augmentation is here. Okay. And instead of here, the augmentation is here. Okay. And then you see that you're already having your matrix here. Okay. So this is your C11, this is your C21, this is your C12, and this is your C22, because this is just the identity matrix. Okay. So this matrix is then just equal to -7, -1, 3, 2. Okay. So you see that the last two elements given in the spanning set is already in the, are already linear combinations of the first two columns, and you are done. Okay. Well, as we said, now, this was just an example of the algorithm that we saw in the last class. Now we are actually going to use such a thing in something that we proved now. Okay. So here's the proposition. Suppose V is, actually you don't need to assume anything on V. So suppose we are having a finite spanning set and a finite linearly independent set. Okay. Suppose S is a finite spanning set of a vector space V, and let L be a linearly independent subset or linearly independent set in V. Then the cardinality of L, you denote the cardinality by this, or do you use this one? The first one? Okay. So the cardinality of this is less than equal to the cardinality of S. Okay. So let's prove this first. Okay. Before we go into anything about, before we promised that we will discuss something about infinite dimensional spaces, right? But let's consider this one first. Let's finish the finite part and let's then go to the infinite part. Okay. So proof. How should we proceed? What's the idea? We are going to do something similar, but so we proceed by contradiction. Okay. That is we will assume that this one is, the cardinality of this one is larger than this one. Okay. And then we'll do something similar to that. That means we would like to write the elements of L in terms of S, and we'll have a matrix for which we can give a similar argument. Okay. A similar argument means that an argument that Monideep has already given, that is, if the number of rows in a matrix is less than the number of columns, then the homogeneous equation always have a non-trivial solution. Always has a non-trivial solution, which was this was a first problem in the first test, right? In the second test, actually, first graded test. Okay. So what we do here, let the cardinality of S be something, call it maybe M, and let the cardinality of L be N, and if possible, let's assume the contrary, that is M is larger than n. Okay. Now, what we will do is to express the elements of L in terms of the elements of S. Okay. Because it's a spanning set, we can do that, right? So suppose S is any doubts, please you can ask me. M right, yeah, thank you. Because we are trying to show that M is greater than N, so it will be opposite. Thanks a lot. Yeah. Thank you. Your name, please? Deepto. Okay, thank you, Deepto. So indeed, we are assuming the contrary, that is M is less than N, and we will show that that's not the case. M should be greater than or equal to N. Okay. So suppose S is these vectors, maybe you can write them as V1, V2 dot 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 Vm, okay, and let L with these vectors W1, W2 dot 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 Wn. Okay. Now, we would like to write W1 as a linear combination of these ones, because S is a spanning set, we are allowed to do that, right? So since S is a spanning set, we may write Wi as C1i Vi plus C2i V2 plus dot 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 plus Cmi Vm, right? Note that we are doing something similar to this. We are writing every column, instead of a column, now think of the elements of this linearly independent set. So we are writing this as a linear combination of the elements of S. So like this one, C1 times the first column, C2 times the second column, was giving you the first column, this one. Okay. So basically, these linear combinations for Wi, if you now put them in the matrix form, this would just look like V1, V2 dot 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 Vm. Okay. This, well, if you have a set of vectors and if you put them in such an order form, you can call this a hypervector. Okay. That's a term often used in the literature, but what we mean by hypervector is not exactly a vector, but it's a set, ordered set of vectors, and we write this in this notation because we would now want to write this one. So for example, when I is equal to 1, we have C11, C21 dot 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 Cm1, right? For I, we have C1i, C2i dot 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 Cmi, and when I is equal to n, for Wn, you have C1n, sorry, 1n, C2n dot 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 Cmn. Okay. So these columns are giving you these linear combinations of V1, V2 to Vm, which is W1, W2 dot 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 Wn. Okay. And now, how should we get a contradiction? So up to this, it's just writing the elements of this linearly independent set as linear combinations of the spanning set. Okay. So now what is the thing which can give us a contradiction? Which one? Of course, yes. We need to get a linear relation of this which is equal to 0. Your name, please? Sandeep. Okay. Thank you, Sandeep. Indeed. So we need a linear combination which is going to give us 0, definitely. And then what we do we write now this thing. So we require, okay, we do not, yeah, we require it for the necessary, I mean for the contradiction. Okay, so we would like to have a set of vectors. Okay, say call this, well, a set of elements a1, a2 to an such that a1 times w1 plus dot 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 plus a set of n elements from the field over which v is defined, such that this is equal to 0 and not all of these are 0, and not all ai's are 0. Okay. So that is, we are looking for a non-trivial solution of, so if you call this x, then we are looking for a non-trivial solution for w1, w2 dot 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 wn, this hypervector times x. This is 0 such that x is not equal to 0. Not all the entries of x is 0. Okay. Now, instead of this, we would substitute this one. Okay, v1, v2 to vm, and this matrix of coefficients. Okay, call this matrix A, say. Okay, so this will give you then v1, v2 dot 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 vm times A times x equal to 0. Okay. Now, this one was this times this, and now we were having this times x. Now, because of the associativity of scalar multiplication, which translate into scalar, I mean associativity in this case of matrix multiplication, it will be that instead of doing this times this first, we could have done this times this first as well. Okay, yeah.
Don't get the part why a1 all ai's will not be.
Which one?
Why all ai's will not be.
All not. Yeah, they are linearly independent. This w1 to wn, but we would like to get a contradiction to the linear independence. Okay. That was the point that Sandeep meant, that now because we assume that m is less than n, we are looking for a contradiction. Okay. So from where the contradiction can come? From the linear independence of the set L. Okay. So if we can show that L is linearly dependent, Mahfuz, are you with me? Or are you not? Okay. So yeah, you are? Okay. So what we are trying to do is that this say w1 to wn, this is not linearly independent. If we could show that, then we are getting a contradiction, because that was one of the assumptions. Okay.
So you are going to show that if n is greater than m, non-zero x will exist.
Yes, right. Okay. So now we are in this situation, that is ax equal to 0, and the question is that whether there exists an x not equal to 0 such that the above equation star is satisfied. Okay. So that's the question. Okay. Excuse me, your name, please. Yeah. Sangam. So could you please tell me now, Sangam, that whether such a thing should exist or not, an x such that ax is, I mean, so what we are looking for, a solution to this homogeneous equation ax equal to 0. Okay. And we have information about A, that A is this matrix. Okay. And x is, we are looking for some vector x which is not quite 0, not all the elements are 0, because if all the elements are 0, then of course this times all zeros is 0, right? So now our question is that whether there should be an x for which this is equal equal to 0? Why?
Because there is
Yeah.
last column is non-zero.
The last column of this, we don't have any information about uh, any of, well, wait a minute. The last column should be non-zero because none of these elements should be 0, right? Because this is a linearly independent set. Excuse me, your name? Yeah, Sumbi. Sumbi, so can 0 be an element in a linearly independent set? Trivially, yes. So if 0 is an element here, well, your name please? Tushyanth. Tushyanth, if 0 is an element here, does it remain linearly independent? Why not?
Because we can put a non-zero coefficient to that.
Yes.
Still it becomes gives 0.
Right. So Sumbi, it's fine. I mean, it's no problem. So what we want to say here is that if we are having a1 w1 plus dot 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 plus an wn, if this is equal to 0, and if this itself is equal to 0, then this times an, I mean, put all the other coefficient to be 0. Okay, put a1 equal to 0, an minus 1 times v, sorry, not v, wn minus 1. Put all this other coefficient to 0, okay, and put whatever you like in at an. That makes this, I mean, that in particular makes the not, I mean, satisfies the hypothesis that not all the coefficients are 0. So a1 to an, if you take this as a tuple, it's not equal to 0 because the last one is non-zero, right? But you are putting all the other coefficient to 0, and this vector wn itself is 0. Okay, so if that is possible at all, so what you are getting a non-trivial linear combination. That is, not all the coefficients are 0, but on the right hand side you are getting 0. That's not allowed, okay, for a linearly independent set. So that's why this cannot be equal to 0. None of the elements here is equal to 0. So in particular, Sangam, indeed that's true that none of, I mean, this entire column, not all of them can be 0. Yes, but from there, does it follow that there exists a solution of this? I mean, your claim was right that none of these columns can be entirely 0. Sure. So think about its dimension. What is the dimension of this? Can you see from there? It is, well, you are writing these ones as a linear combination of this, okay? And these columns are giving the linear combinations, okay? So in each column, there are m entries. That is, there are m rows and n columns. So this is an m cross n matrix, okay? M cross n times x equal to 0, okay? So we are trying to look for a solution to this, okay? And now, Sautrik, can you tell whether there should be a solution to this equation or not?
No.
A non-trivial solution? No? A is a non-zero matrix, of course, yes.
So it has only a trivial solution on x equals to 0.
It has only a
Trivial solution on x equals to 0.
a trivial solution at x equal to 0, that's there. But is there any other solution? The question is that whether there exists a non-trivial solution such that this one is satisfied. We have some assumption on m and n. What was that? Excuse me. No, Mahfuz. I'm talking about him. Yeah. Your name is? Amol. Yeah. Amod or Amol? Amod. Sorry. So Amod, can you tell whether there exists a solution for this or not? There should. Why? Wait. It's Amod's turn. the number of rows. Is the number of rows more than the number of columns? It's the opposite, right? It's an m cross n thing, and we assume that m is less than n. Okay. So you are having a matrix of this form, okay, a rectangular form where this is smaller than this. Note that there could exist one pivot in each row and in column, at most one pivot, right? So you will have the number of pivots always less, right? Less than the, so if this is m cross n with m less than n, then you cannot have the, a full number of pivots, okay? And that will ensure that you will have a non-trivial solution always, okay? So trick, is this all right? We just saw an example before this. We had a 2 cross 4 matrix. We row reduced it. We got pivots in both of the, in 2 columns. Okay, but if we have, well, if we just have taken this 2 cross 4 matrix, what Manideep already suggested, we are having the pivots only in the first 2 columns, right? So you put so what I want to say is that you are having some free variables to put arbitrary values there, okay? And that means you are always going to have a non-trivial solution to this if m is less than n, okay? Yes? Yeah, okay. So that means this is giving us a contradiction, right? We assume that m is less than n. That is leading us to a non-trivial solution of this, okay? Now, a non-trivial solution for this one would mean that you are having a non-trivial x for which this is satisfied. Now, if you are having a non-trivial x, that means you are having a non-trivial linear relation which is giving you 0, which is not possible, right? Because W1 to Wn are linearly independent, okay? So, non-trivial solution to Ax equal to 0 implies a non-trivial relation, okay, where what was x? X was this a1 dot 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 an. The coefficients of this the things in the linearly independent set L, okay, and this implies that there exists a non-trivial relation a1 w1 plus dot 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 plus an wn equal to 0, okay. It's a contradiction because this is a contradiction as L is linearly independent, okay. So that means m cannot be smaller than m should be larger than or equal to n, okay. So m is larger than or equal to n, that is L is less than or equal to S, okay. The coordinate of L is less than or equal to S. So, Shautrick, you can remember this just by remembering less, okay. Less starts with L, ends with S, and you have this, okay. Yeah. So now remember this L and S, remember the picture of the pig, mouse and elephant. So what these two corresponds to, L and S? The left hand, that is a mouse, and the right hand, that is the elephant, okay. So the bases should sit in between them, okay. And now we are in a perfect situation to say, okay, so suppose we're having vector space with two different bases m and n of coordinate m and n, okay. So if you are having, so suppose we're now given a vector space V with basis B1 such that the cardinality of B1 is equal to m and another basis B2 such that the cardinality of B2 is equal to n. Okay. Now, what can we say about m and n? Exactly, because these are, I mean, once you can consider this as a linearly independent set and this one as a spanning set. Okay. So, then you get that B1, the cardinality of this is less than equal to B2. And the second part, swap it their descriptions, that is a basis is a linearly independent spanning set, right, ordered linearly independent spanning set. Yes, Shukrita. Well, hypervector, this is just a notation for our ease of writing. Okay, we couldn't have used that notation at all. Then it is just a linear combination of V1, V2. So this matrix is nothing but a set of linear combinations among the hypervectors. Okay, so we are not defining a space of hypervectors. By hypervector, we just mean an array of vectors. Okay. It's a set of vectors, and then if you are writing the linear combination of this set of vectors as the columns of this matrix and working with this as just matrix multiplication, it's fine. I mean, you can proceed in that manner, because on the right hand side whatever you do, that makes sense, because what is this? This is a linear combination of the linear combinations of this one. So instead of using this notation at all, we could have written that this we could have written a double summation over this summation Cij Vj that was giving you Wi, right? And then we could have written that we are considering a sum over ai's now, I running from 1 to n, and there j was running from 1 to m, such that this is 0. But it would have made life only complicated, okay? Because we would have done the same work, but there, I mean, from this relation, we had to get out this matrix equation. Okay? So it is just notational convenience, nothing else. By a multiplication of a hypervector with a matrix, we just mean that we are considering this as a row vector multiplying with the columns, and considering this multiplication, that is a1. So suppose the first column is, no, we should not use a1, a2. Okay, so c1, c2 dot dot cm. Then this times the first column would be c1 v1 plus c2 v2 plus dot 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 cm vm. Okay. And then this times this is nothing but having a set of linear equations like this one, where these ai's are the variable, that is the entries in this x. Okay. Linearly independent set should have a cardinality lesser than a spanning set. Okay. And then this argument with the basis was, so the as a corollary we can write here that as a corollary, let V be a finite dimensional space. Okay. And let B1 and B2 be two bases of V. Okay. Then the cardinality of B1 and the cardinality of B2 are equal. Okay. And this cardinality we call the dimension of the vector space V. Okay. So dimension of V is defined to be the cardinality of B1, or which is equal to the cardinality of B2. So basically dimension of a vector space is the cardinality of its basis. Okay. And we just proved that it is well defined. Okay. Yeah. What? Yes, and how do we define a finite dimensional space? Yes, how did we define? What was the definition? The coordinate of basis? We haven't defined basis while we define finite dimensional vector spaces. Exactly, a finite spanning set. So if it has a finite spanning set, we called it a finite dimensional. But we haven't defined what a dimension is. Okay, now we are defining that it is a dimension of a basis. So the last corollary maybe, that is a finite dimensional vector space will have, all the subspaces of finite dimensional vector space is finite dimensional, and the coordinate of the basis of any subspace of this is less than equal to the coordinate of the basis of V. Okay. So that's the last corollary of today's class. Let's draw this and end the class. Corollary, let W inside V be a subspace, let W be a subspace of a finite dimensional vector space V. Okay, and before we can write it, so then dimension of W is less than equal to dimension of V, and the equality holds if and only if W is equal to V. Okay. So since it's a corollary, I wish the proof should come from you. Could you please tell me how should we proceed? Where should we start? With the basis of W. Okay. So at first, suppose it is the basis of W. Well, suppose at first that W is also a finite dimensional subspace. Okay. We'll check later whether it can be infinite dimensional or not. Okay. So suppose W is a finite dimensional subspace. What does that mean? It has a finite spanning set. And now you have some more precise thing after we wrote that. It has a basis. It has a finite basis. So what can you say about the elements of the basis? Yes, and?
We can say that basis of W is linearly independent.
Yes, the elements in the basis of W is linearly independent. Now if you look at them as elements in V, do they remain linearly independent? Yes, because you are allowing all kinds of linear all the coefficients, you are not restricted to something when you are considering this as a subspace or when you are considering them as an element in V. You are allowing all the linear combinations in both spaces, right? So if there is no non-trivial linear relation among them here in W, there cannot be a non-trivial linear relation if you look at them as elements of V. Okay. So since a linearly independent set in W is also linearly independent in V, a basis of W is, remains linearly independent in V. Then what? Yeah.
This will be less than equal to that.
Okay, sure. That's of course work, because this is a linearly independent set, that basis of W, and if you consider now a basis of V, that you can consider as a spanning set, and we just saw that the linearly independent set has lesser cardinality than the spanning set. So we are done. Okay. Now, okay. So if consider this as L. So since a linearly independent set is also a linearly independent basis of W, call that L maybe. Okay. So then if S is a basis of V, then we know that the cardinality of L is less than equal to the cardinality of S. Okay. And this is the dimension of W, this is the dimension of V, so we are done. This is the dimension of W and this is the dimension of V. So we have indeed this equality, okay, inequality. Okay. Now what happens if W is infinite dimensional? Is that possible? Why not? Right, and then? Exactly, yeah. So in particular, among that infinite, well, what is a linearly independent? Maybe we will start the next class from this question. That is, we will revisit this again, because this is actually a rather important question if you look at infinite dimensional vector spaces. So what is an infinite linearly independent set? Wait a minute, Sumbi, can you tell me what is an infinite linearly independent set? You know what is a linearly independent set, right? There is no non-trivial linear relations among its elements. Okay. Now that is for, I mean, we defined, like we took V1, V2 to Vn and we said that there is no non-trivial linear relation among them. This we will call, then we will call V1, V2 to Vn a linearly independent set. Now suppose we are having an infinite set, when do we call that linearly independent? For example, consider this set, 1 x squared dot dot dot. Okay, is this set linearly independent? This is x is an indeterminate, a variable. Okay, so the question is whether this is a linearly independent set or not. Yes. So at first you can just consider maybe up to xn. Okay, is this linearly independent? You have suppose you are having only n elements. Okay, we are considering its linear independence over some field, say R. Okay, question is whether at first this set is linearly independent. Yeah. Yes, it is a set of polynomials in of degree n with coefficients from R. Then you are asking whether there exists a polynomial which always takes value 0, whatever coefficients, I mean, whatever value of x you put there. Does there exist such any such? So that is, I am asking whether there exists fx equal to a0 plus a1x plus dot 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 plus anxn, such that fx is identically 0. That means whatever value of x you put there, it will just give you the 0 output. Okay. Can that happen? Why not? Yeah. Abhijit? We are considering at first whether this is linearly independent or not, this set, okay, before we go to infinite sets. Okay. So that would mean, I mean, if this is not linearly independent, there should be such a linear combination which is equal to 0 for all values of x, right? I mean, because x was an indeterminate, that means you can put any values of x there and check whether this is giving us a 0 polynomial or not. So the question is that if all this ai is considered in R or some field C as well, or for the moment take them in R, suppose. And the question is whether there exists this a0, a1 dot 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 an such that this is equal to 0 for all x in R. Does there exist a0, a1 dot 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 an such that this happens? Yeah? It is? Why? Yeah. Well, if this there is a I mean, if put all zeros, then it's fine. I'm asking that whether there exists a non-trivial solution.
There cannot be non-trivial solution that satisfies all for all x.
Exactly. So not all zero, not all zero. Yes, there cannot be a non-trivial solution. That's why. I mean, that's what I'm asking. Why there can't be any non-trivial solution? So all we are trying to is to prove that this is a linearly independent set. Orkodeep? Yeah? There doesn't exist? Yes, the question is why? How can you say that?
So
Oh, wait a minute. Yeah.
by back calculating the AIs from the fx,
Back calculating? Yes. How do you back calculate it?
if x equal to 0 always, we can back calculate that all the AIs in the system.
How do you back calculate? What is the procedure?
So if we take f of 0 to f of n,
Yes.
f of 0, f of 1 to f of n,
Yes.
that gives us a matrix of f.
Right. Yes.
And we see that if fx is always 0, then a0 and 2an is always 0. And by contrapositive
So you are arguing about, I mean, by invertibility of some matrix, right? That matrix has a name. It's called van der Waals matrix. Indeed, that's a valid argument. Any other way to do? Yes.
I think it's because of the one we have a naught to an, we have the cardinality of the an to be greater than the dimension of x.
The cardinality of?
A naught to this all set or
Yes.
value, so we greater than
So you said that n is larger than the number of solutions of this. That's called the fundamental theorem of algebra. That's also one way to proceed. Any other way? Yes.
if we assume there exists a non-zero non-zero AI,
Yes.
and it should be true for all x belongs to R.
Yeah. Again,
It should be true for all x belongs to R.
which should be true for all x?
Like if you assume AI x to the power I is
Yes.
not equal to 0.
ai times x to the power I is not equal to 0, right? Yeah.
So if AI is not equal to 0, then you can just put x to be anything like 1.
Okay. Yeah. Sure.
So that would imply 1 equals 0. So that's not possible.
No, but a polynomial will have some roots, right? So.
The contradiction is what I'm saying.
So I think you are arguing in the same manner as Nitish just did. So you're comparing the number of roots with this n. Yeah, and that is, I mean, implicitly you are using the fundamental theorem of algebra. Now can you use some analytic tools? Exactly. Yeah. So your name again? Yeah. Anvesha. Okay. So indeed, that's you can take the derivative. Since it is always 0, I mean its derivative is also 0, right? And you can take the first derivative. I mean actually you can start with the nth derivative, single this out, okay? Show that this is equal to 0, then show that n minus 1 is equal to 0, and so on. So there are various ways of showing that all the coefficient should be 0. Okay. I mean, there is no non-trivial linear relation among them. So in particular, this is linearly independent. Okay. Now suppose you remove this one and you take as I mean not only xn, say xn plus 1, xn plus 2, x power a Google and more. Okay. So does that set remain linearly independent? To understand that, at first you have to understand what we mean by an infinite linearly independent set. We defined it in the last class. So anybody recall any of you recall the definition of an infinite linearly independent set? Very good, Snowmi. Any finite subset of this, if you take it, it should be linearly independent. So what is an infinite linearly independent set? For any finite subset of which the only linear relation among so for any finite subset, say S of which the only linear relation among the elements of S is trivial. Okay. So in particular, if you take any set of indeterminate, I mean this x, so any powers of any set of powers of x, any finite subset, then we just showed that they should be linearly independent. I mean, what it should be, you can take some x power n common out of that, and then you are having such polynomial, right? And suppose you do not put a value where x is equal to 0. Well, x equal to 0 is just one value, right? So for everything else, you are just having, I mean, just considering such an equation which should be 0, right? If there would exist such coefficients, and we just showed a while ago that that's not possible. Okay. What we mean by an infinite linearly independent set, and that just means that whatever be that set that you are considering, any finite subset of it should have only the trivial relation among its elements. There is no other non-trivial linear relation among its elements. That we call a linearly independent, infinite linearly independent set. Now let's come back here to this question, that is, if W has a basis which is an infinite linearly independent set, then we are in that case, right? We are in such a case, and here is an infinite linearly independent set. So if you take, I mean, now if you cut it at any place, does it remain linearly independent? So what I want to say is that suppose you cut it at xn, okay, and you are considering only this, does it remain linearly independent? And if you replace these powers of x with some other functions, as you just mentioned, does that remain linearly independent? It is, because take any finite linear combination of the elements of this. Actually, take the linear combination of all these elements. It's still a finite set if you are cutting at a finite place, right? So that still remains linearly independent. Okay. So now, having an infinite linearly independent, I mean, if it is dimension W is infinite, that would mean that you are having an infinite linearly independent set. Cut it at some place which has whose cardinality is larger than the dimension of V, and you are going to have a contradiction, right? Because that is a linearly independent set whose cardinality is larger than the dimension of V. So you are still comparing finite things. I mean, this still makes sense, this still makes sense, because you are having a finite linearly independent set sitting inside V whose cardinality is larger than the cardinality of its dimension. Okay. Shumbi, is the argument clear to you, or should we repeat it? Yeah, sure. So up to this, for finite dimension, is this fine? with you? Okay. Now we are considering the case when dimension W is infinite. Okay. That means W has an infinite basis. Okay. That is in particular an infinite basis would be an infinite linearly independent set. So as we just said that if you cut infinite linearly independent set, that is if you take any subset of a linearly independent set, it's still linearly independent. So take a finite subset of the linearly independent set that is a basis of W such that that finite set has larger cardinality than the basis of V. We are considering a finite dimensional subset V, so a finite dimensional vector space V, sorry. So this one is finite, and if this is infinite, we can take a larger linearly independent set in V which is larger than its basis, any of its basis. Okay. So that would mean we are getting a contradiction to this because this is your linearly independent set. Okay. And this one is now your basis. A basis is a spanning set as well, right? But if this one is larger, you are going to get a contradiction to this one. Okay. All right. Sanam, Dushyant, is it fine? Okay. Thank you. So that's the last thing that we do in today's class. In the next class, as we said, we will start from this question again. We'll review this and we'll proceed to see the infinite dimensional cases only in one class, and then we'll move on. All the best for the exam. Thank you.